Yes, welcome to all. Today's discussion is the final part of the Doppler effect. In this part, we are discussing when the observer in rotations or when the source in rotations, so either of them. So, in this part, we are discussing when the source are in rotation in a circular path whose radius is r, and with the angular velocity. We have the angular velocity of the source is omega, and the source is moving. Suppose it's a radius of the circular path is O, and our observer O is our observer. This is our observer. Now our observer is at rest. Now it is not moving. So this is our observer which is at rest, and source is moving anti-clockwise in the circular path. Let us suppose when the source is moving toward this one. So here the observer and the source, this circular path and the observer are far away. That's why the distance between them, we assume that the straight path and this path, angle between them is negligible. So it only possible when the observer is far from this circular path. So let us suppose the observer is at rest and our source is moving toward the observers with a velocity Vs. Vs is the velocity of the source, and when the source is lower part, the velocity of the source is along this one. So we are discussing both the cases. In one case, when the source is moving toward the observer, the apparent frequency will increase, and when the source is moving away from the observer, our apparent frequency will decrease. So one by one we will start. So when the first part, when the source is moving toward, this is our observer, the source is moving toward the observer. Moving towards the observer, and the observer is at rest with a velocity Vs. Vs is the source velocity. So we know that the distance between, this is our observer, this is our source, distance between them is decreasing. The apparent frequency heard by the observer will increase. So here V is the velocity of sound in air, velocity of sound in air, and therefore the apparent frequency. Apparent frequency will be V divided by, since our source is moving toward the observer, therefore denominator should be smaller than the numerator. V minus V is multiplied with the true velocity, that is original FO is the original frequency of the sound when both are at rest. When both are at rest, F0 will be our original frequency. So it means that our apparent frequency will, in that case, will increase. Now in the second part, in the second case, when the source is in the lower portion of this circular path, it means that when the source is moving toward the right and observer is at rest, so the distance between them is increasing, and our apparent frequency which is heard by the observer will decrease. Now for that, since our source is moving away and the denominator should be greater than that of the numerator, therefore our apparent frequency will be, in that case our apparent frequency, apparent in that case when the source is moving away from the observer, our apparent frequency will be V divided by V plus velocity of the source multiplied original frequency. So in this way this is the decreasing, and the apparent frequency heard by the observer is less than that of the f naught. In that case, the apparent frequency heard by the observer is more than that of original frequency. And now in second part, we brings the observers in the moving in a circular path, and our source is outside and at rest. And another case when the observer is moving and our source is at the centers, and when our source is moving in a circular path and our observer at rest at the center of the circle. Let us discuss one by one. Now look at the pictures. When our source is revolving in a circular path whose radius is r and angular velocity is omega, and our observer which is at rest, which reside at the center of the circle. So what would happen? In that case? So there will be no apparent change in frequency, no different frequencies as that of the original frequency. Here original frequency and apparent frequency will be the same ones. So this is explained in these figures, and our sources is revolving anti-clockwise direction with a velocity of vs. Our observer is at this one, and this makes an angle 90 degree. So we know that when the center is joining to the any point of the circumference, and at the meeting point, if we draw a tangent, it will make an angle 90 with the radius vector. So this is our radius vector, this is our tangent, and in any situations when the source is moving in a circular path and it has directions along the tangent of the circles, so that's why the angle between them is 90 degree. So since our observer at the center, our source is here, if you take the component of Vs, so Vs, the component of Vs along the observer will be Vs cos 90 degree, Vs cos 90 degree. So Vs cos 90 degree will be 0. So in that case, so Vs cos 90 degree will be 0. Therefore, there is no effect of the moving source in a circular path. So we also know that the value of the frequencies in that case apparent. If I write the value of the frequency when the source is revolving, when the source is moving, we have V divided by V plus minus here Vs cos 90 degree in that case. So Vs cos 90 degree into original frequency. We know that Vs cos 90 degree is equal to 0. Therefore, our value becomes V upon V into V naught. You know that the apparent frequency will be original frequency. It means that there is no change in frequency when the observer is at rest and our source is revolving in a circular path. Same situation would happen when our observer is revolving and our source is at rest. In that case also, the apparent frequency and original frequency will be the same one. And let us show in this picture. Now this is second situation when our observer is rotating. This is our observer, two positions. The observer is rotating with angular velocity omega, and its velocity is v naught. Okay, and our source is at rest since so here the source and observer are far away. Okay, when the source are far away, the angle making by this and by this horizontal with this line joining the observer with the sources is approximately negligible. We can say that around 0 degree. So we can no need to take the component of the velocity of the observers along this one, because the source is far away from this observers. So now in the first case, in the above case, when the observer approaching toward the source. Now in the first case, when the observer is approaching uh, towards the source. So in that case, our apparent frequency will be more than that of the original frequency, since the source is addressed and our observer is moving toward the sources. Therefore, our numerator would be v plus velocity of the sound in air plus the velocity of the observer divided by v. This fraction is more than that one, and if you multiply it with this the original frequency, and I will get the apparent frequency. This is our apparent frequency. So our apparent frequency in that case more than that of the original frequency. Now in second situation, when the observer is in the diametrically opposite that of the original positions, and it is directly away from the source. Now its a velocity, let us suppose v naught. Since our observer is away from this one, moving away from the sources. This is our source, this is our observer moving away, and the distance between them is more and increasing. Okay, it is increasing with times. Therefore, our apparent frequency will decrease. So therefore, in that case, when the observer moving away from the source, therefore the apparent frequency will be v minus v naught. Our numerator should be less than that of the denominator. So multiply this one. So in both the situations, in one situation our apparent frequency is increased, in second situation our apparent frequency is decreased. Now in third situations, when the source is at the center of this circular track of the observer, in that case the apparent frequency will not change. Your apparent frequency and the true frequency will be the same. Now look at these situations when the observer is moving in anti-clockwise direction. Our source is at center, which is at rest. So our source is at rest. When the source is at the center of the circle, yes, the center of the circles, you know that this is the new picture of this ones. So velocity of this observer, which would be tangential, and our source is at the center, angle between them this one. If I take the component of v naught along this one, okay, this is our observer is here, this is our observer at this point, and our source is this one. If you take the component of v naught along this one, it will be v naught cos 90 degree. So it means that it will be 0. So if I find using this apparent frequency in earlier case, which we have did in earlier parts, so we have since our sometimes it looks like the observer moving away from the sources, and sometimes moving toward this one. So here the apparent frequency will be v plus minus velocity of the observer cos 90 degree divided by velocity of the sound in ear multiplied v naught. So we know that this value comes out v plus minus 0 divided by v. So here into f naught. So what comes out? Okay, it comes out only v upon v into v naught. So we got only the V naught the value. Therefore, apparent frequency will be true frequency of the sound which is heard by the observer. Now let us do a numericals under these situations. So we will be better to understand these situations. Now look at this questions. This is the question. A source is a whistles. A whistles making a sound going in a circular path, and its a velocity. Well, velocity of the whistle is 30 meter per second, and the original frequency of the whistle is 540 hertz. v minus velocity of the wind, v omega. So this is the case of when the medium, so that is the air, is moving. Now let us do one numericals under these observations on the formula, and let us start. Now the general equation of the Doppler effect in all cases when the medium, when the source and observer are in motion. Now the formula will be, the apparent frequency will be velocity of the sound in air, still air, plus minus velocity of the wind, plus minus velocity of the observer divided by v plus minus velocity of the wind minus plus velocity of the source, velocity of the source multiplied the original frequency of the sound which is heard by the observer. So this will be our apparent frequency. Apparent frequency now let us do one numericals under this observation, under this formula. Now this is the questions. A person going away from a factory on his scooters at a speed of 36 km per hour. The velocity of the observer which is moving away from it. This is our factory. Factory is at rest. It is at the source of sirens. And observer moving away with a velocity of 36 km per hour. If you convert this meter per second, we have to convert kilometer 1000 divided by hours. Hour can be written 60 into 60. The value comes out 36 into 5180. So after solving this, it comes out at 10 meter per second. 10 meter per second is the speed of the scooterist. Now here our source, velocity of the source is at rest. Source is at rest. Since wind is blowing, our wind is blowing along the direction of the observer with a velocity of, this is wind velocity. Yes, velocity of wind. Velocity wind is blowing along the direction of the scooters at a speed 36 km per hour. It is also 36 km per hour. Wind velocity is the same as that one. 36 km per hour can be converted in meter per second. It will be 5 meter per second. Earlier it is 36 km per hour. So now since wind velocity is along the direction of the sound velocity which is going toward the observer. So we have to make some changes in the equation of the Doppler. So therefore our apparent frequency will be v plus wind velocity. Our observer moving away from the sources, so we have to subtract the observer velocity divided by v plus v omega. Our source velocity is rest. Source is at rest. Therefore, no value putting is in the denominator. Multiplied original frequency. Our original frequency is 600 Hz. So this is 600 Hz. So the apparent frequency heard by the motorist on the scooter will be, velocity of the sound in air is 3. Velocity of sound in air is 340 meter per second. So now 340 plus wind velocity. Wind velocity is 10 meter per second. Observer velocity also 10 meter per second, and divided by 340 wind velocity plus air velocity multiplied the original velocity of the sound, which is 600 Hz. Now if you calculate this value, value comes on -10 plus 10. 340 divided by 350. 350 into 600 hertz. Now this value comes up 582. If you calculate this one, it comes up 582. 582.86 hertz. So this will be our final answer.